Okay, so now we'll talk about the charge is quantized. So, so electric charge is quantized, restrict to certain values. The charge of particles can be written as n times e, n times e. N is a positive or a negative integer. We can have a positive charge or negative charge. And E is the elementary charge. So any positive or negative charge Q that can be detected can be written as n equals QE. N equals to all integers. Integers actually include zeros, and it can be electrical neutral. And E is the well-known constant, which is called the elementary charge. We will face this constant throughout the whole course until the end of the chapter in this semester. So E is 1.602 times 10 to minus 19 Coulomb. Usually, we can use 1.6 times 10 to 19 is just fine. Maybe in the latest chapter, then some of the solution you see you will use 1.602, but generally I will only use 1.6 is sufficient, because O2 here is around 1 or 500 of this 1.6. So this O2 is not really that important unless you are a scientist. Then you may probably need more significant digits, but 1.6 times 10 to minus 19 Coulomb is good enough. And as you have learned in the chemistry class, so we know some of the fundamental particles known as the electron, proton, and neutron. So the electron has a negative E, proton has positive E, neutron have a zero charge, electrically neutral. So this is nothing special. It only means that we can only have just say plus 10E minus 6E or the integer multiple of the elementary charge. You cannot get something like 3.57E, 1.5E, or whatsoever. Okay, so charge is quantized is nothing special, which means that you cannot break an electron into even smaller fundamental particle. Actually, for the proton and neutron, you can even break it into smaller fundamental particles. I will show you just a few slides later. But in high school level, what you have learned is electron, proton, neutron are the fundamental particles. But it doesn't really matter. I just show you some information about the standard model of the particles later on. So here's a checkpoint, very simple. So initially, sphere A has charge of minus 50E. So let's say we have a sphere A. It has minus 50E. So, and sphere B has a charge of plus 20E. So the sphere are made of conducting material and are identical in size. If the sphere then touch, what is the resulting charge on sphere A and sphere A? On sphere A. So at the very beginning, both sphere A and sphere B have some initial charges. So after they touch, and it asks you what will be the resulting charge on sphere A. And of course, you will know the sphere B, because you know not only the charge is quantized, but also charge is conserved. You cannot create or vanish a charge. So after they touch, and another important condition is that they are identical in size. as long as they are identical in size, which means that after they touch, and then this wire, suppose there is a small wire connecting them, or just move them to touch, and then they just separate afterwards. Then, of course, there will be some charge going from either from sphere A to sphere B, or the vice versa. And as much as this condition is they are identical in size, which means that after they touch, they will have same amount of charge on them. They have same amount of charge on them, or there will be the same charge density over the surface. So this question will be easy, which means that the total charge here is nothing but minus 50e plus 20e, which is a minus 30e, right? So then this minus 30e will be separated equally on both sphere A and sphere B, which means that there will be minus 30e over 2, which is minus 15e on sphere A and also on sphere B. So this is the answer to this checkpoint question. So this is simple. And let's see another sample problem. So here we see that it says the nucleus in an iron atom, tier, has a radius of about 4 times 10 to minus 15 meter, and contains 26 protons. What is the magnitude of the repulsive electrostatic force between two of the protons that are separated by this distance? So as long as you know the high school chemistry, you know for a atom there will be nucleus and also some of the electron. This is the nucleus, and the nucleus will possibly have some proton and neutron hit there. We don't actually know how many neutrons are there, but it doesn't really matter. It concerns about the electrostatic force, or the repulsive electrostatic force between two of the protons. Let's say one of the proton is here, and another proton is here. So because it says the iron atom has a radius of about 4 times 10 to minus 15. So it asks you about the repulsive force between the two protons, because both of them are in a positive E charges on them. So there should be a Coulomb force repelling each other. So this is pretty easy. You just need to use the Coulomb's law, F equals K times Q1, Q2 over R squared. So K is 8.99 times 10 to the 9th power times E is 1.6 times 10 to minus 19, just mentioned. And then square, because both Q1 and Q2 are positive E. And R square is nothing but 4 times 10 to minus 15, and then square, quantity square. So this F is 14 Newton. So this question is pretty easy, but the point here is not to show you about the Coulomb's law. It shows you some hardcore physics later on using this simple question. So this follow-up question is, what is the magnitude of the gravitational force between those same two protons? So still the same iron atom, and it asks you about the gravitational force between them. And if you have learned the physics 1, or if you have ever learned some high school physics, you will know the gravitational force. Of course, you don't actually need to know it for this course, but it just show you some hardcore physics later on, so you don't need to worry. So the gravitational force is nothing but G times mp square over r square. So this is the gravitational force from Newton's, Isaac Newton's. So G is the gravitational constant, and mp is the mass of the proton, and r is of course the distance between them. So G is 6.67 times 10 to minus 11, and then times 1.67 times 10 to minus 27 kilogram, and over the same distance r, which is 4 times 10. This is quantity square times 10 to minus 15 quantity square. So yeah. So here the force is nothing but 1.2 times 10 to minus 35 Newton. So this is still another easy question. So, but actually, it just want to show you that this attracting force between this repulsive force between these two protons are 14 Newton, and then the attracting force between these two protons are just 1.2 times 10 to minus 35 Newton, which is much smaller. Let's say this is F repulsive R. This is FA. So this is much smaller than FR. So you may ask why the atom can be whole like that? Why the electrostatic force will not just distract the whole nucleus? Why the proton with a positive charge can hold together in such a small radius, such a small distance there? Because using your physics knowledge, you cannot imagine other forces that are attracting them, that are holding all the proton there. The neutron is okay. The neutron is electrically neutral. But for the proton, they have a positive charge, and you consider two protons with the distance of the radius of the nucleus, but not even mentioning another proton that are close together. So why? And actually, maybe in high school physics, the teacher may tell you that there are 4 types of forces in the universe. One type is the electrostatic force, electromagnetic force. I mean electromagnetic force, 电磁力, magnetic force. So you will learn it in this semester. So it includes the Coulomb's force and also the Lorentz force, which you will learn in chapter 28. And another one is the gravitational force. Gravitational force, 重力. So you should have learned it in high school physics or physics 1. Yeah. And there will be two another type of forces. One is known as the weak force, and another type is called the strong force. Okay, so, ouch. Wow. Can you hear some strong noise? Probably my office is next to my office is under construction. So if you hear the noise, probably we need to move to another place to resume. If you really hear that, I'm not sure whether Zoom can filter out the construction noise, but yeah. So please feedback to me if you hear too much noise. Yeah. So there were weak force and strong force, and So you will not learn it in this course either, because there are some hardcore physics. These two kind of force is only acting between some fundamental particles. So for the hardcore physics, we have a standard model of elementary particles known as the quarks and leptons. And actually, the quarks and lepton can form the proton and neutron. And what I know is that the gluon tried to connect the proton together. So this type of, I'm not sure whether it's weak force or strong force, try to hold the nuclei together. So another point is the charge is conserved. So So actually, you cannot create or destroy a electron. So the only reaction acting to the electron is something like the electron and the positron can join together and then eliminate some power. And maybe some power will generate some electron and positron. So they are known as the antimatter, 反物质 antimatter. And this is called the positron. The positron. Positron. This is called the 正电子。正电子。So maybe we can talk about this later. And no feedback? You don't hear noise? So let me continue, and maybe I need to try to find another room to continue for the next hour. So let me finish. If there is no feedback, let me continue to finish off this additional example. So here, three identical conducting sphere initially have a following charges: sphere A 4Q, sphere A 4Q, sphere B minus 6Q, and sphere C 0. So sphere A and B are fixed in place with center-to-center separation that is much larger than the sphere. So two experiments are conducted. In experiment 1, sphere C is touched to sphere A, then separately to sphere B, and then it is removed. And then we have another experiment. What is the ratio of the electrostatic force between A and B at the end of the experiment 2 compared to the end of experiment 1? So this is not difficult. So let's see. At the very beginning, for sphere A, sphere B, and sphere C, they have 4Q minus 6Q and 0 charges on them. So for experiment 1, sphere C is touched with sphere A and then separate, which means the total charge on both A and C are equally distributed among them. So after A and C are touched and then are separate, they both have 4Q plus 0, which is 4Q, and then over 2, which is 2Q. So we have 2Q minus 6Q and 2Q after A and C are touched. And then sphere B and then to sphere B, which means sphere C will then touch sphere B. So the next step is C and B attach and separate. So minus 6Q plus 2Q will be minus 4Q, and then equally distribute to both of them. Then it will become minus 2Q here, and then 2Q here. So this is the final situation for experiment 1. And for experiment 2, initially they still have 4Q minus 6Q and 0 charges. And yeah, here, let's see. So now sphere C is touched with sphere B first. So C and B are touched. So which means that minus 6Q plus 0 is minus 6Q, and then divided by 2 is minus 3Q. So both of them will have minus 3Q and then 4Q here. And then the next step is C and A are touched. So we have C and A attached, and then which means that 4Q plus minus 3Q is Q. So it will become Q over 2, and then minus 3Q. Okay, so this is the final situation for experiment 2. So it asks you about the force between A and B. Force between A and B. And of course, you know the force is proportional to Q1, Q2, because the distance are the same, so we don't really consider about the distance. So we only consider about the charges. So let's say F1 is proportional to QA and QB. So we have minus 2Q, minus 2Q. So probably take the absolute value here. So we have 2Q times 2Q. So proportional to 4Q squared. And then F2 is proportional to Q over 2, Q over 2. So Q over 2 here, Q over 2 here. So proportional to Q squared over 4. So the ratio of the electrostatic force is F1 over F2 would be 4Q squared over Q squared over 4, which is 16. So this should be F2 over F1. So F2 over F1 should be 1 over 16. Or you can write it as 0.375. So this would be the answer. And yeah, so this is the end of this chapter.